All right, thank you very much. So today I'm going to talk about what we're doing with robots. I don't have any new or exciting robots to show, so sorry for that, but some exciting things getting done. So the first point I wanted to make is that really in planetary exploration now, it's not so much about the autonomous navigation. We spent a decade trying to get robots to get from A to B. And now, of course, we all see in the self-driving car area, but in off-road as well, these systems are very capable to travel through the roughest terrain, to do that at very high speed. I'm just showing a little bit of video here. This is obviously an ATV. The software it's running is the same software that runs on our Zoe robot. It runs a lot faster because we have big GPUs and things like that we won't have in space. But the same idea, the work that we did with Zoe, getting that to navigate autonomously, allows us to go, this video is showing 25 miles an hour, something like that. So getting from place to place is not the challenge. There are still some challenges in doing that with limited resources and computing. But the challenge that I want to talk about is what the robots do. And in particular, I'm going to argue that we're ready to move from robots that make specific measurements, collect data for scientists, and sort of act as tools, to systems that are able to do more systemic modeling to take those observations and decide what to do with them, and then what to measure next, and so on, to build up models that, again, are useful data for scientists, but are not kind of directed at that individual action level. So I'm thinking about exploration as an information gathering activity, and we want our robots to be able to autonomously gather information. So again, we have planetary robots that are amazing. They have so many instruments and capabilities, but keeping them productive is actually a big challenge. Because of the reliance on the ground to give a lot of direction, to check actions, to check results, to verify data, that introduces some delays that affect your productivity. Of course, this is mainly dictated by the communication rate and the bandwidth that we can get to these planetary rovers. And even to rovers on the moon that we've been looking at here, I know there's not the delay, but there are still bandwidth limitations. These robots can generate much, much more data than we can get back to Earth. So many pictures. So what's still difficult here is being able to collect the data, verify that it's correct, knowing how to interpret the data, and deciding what to do with it next. If we're going to increase our productivity, these robotic systems are going to have to be able to do these things to some degree autonomously. I mean, we're not going to send robots to Europa and not hear from them for decades till they tell us they found life, but we want them to be as productive as possible. So the work that we've been focusing on has to do with field geology and enabling that in a robotic system. So if you go out to the field with geologists and watch what they do for a while, and I've spent a lot of time watching field geologists trying to understand what's happening, they tend to wander around. They have a lot of prior knowledge and prior experience that they're applying. But unlike when we direct a robot on another planet and we say, go to this exact location and measure this exact rock, field geologists are kind of wandering around looking at things and replanning and rescheduling constantly. And in part, that's because what they're trying to do is not understand necessarily one rock, but their real goal is to build a map, a model to understand, the development of an area or the physical processes going on. So they don't have just one goal in mind. They have many goals that are going to all come together as they interpret this area. So we'd like robots to be able to do that as well, right? Make your robot act like a field geologist. So we've been taking this approach, we called it hypothesis mapping, but really the idea is to embrace the map as the goal of the robot, and not embrace specific locations and places and individual measurements. So we want to have information that comes from our scientists, maybe their initial hypotheses of what the map or model of the site should be, also prior information from remote observation, remote sensing. And then with that map, we want to do some planning and decide where are the most effective places to take measurements. And again, not specific places, but this area, that area. You know, the 80-20 rule applies here. You don't necessarily have to get to the top of the mountain to learn enough about it to be ready to move on to the next thing. So we want to do some planning on what our observations will be, and we want to make sure those observations that the robot collects really count and update the map in ways that are going to improve it, maximize the information gain, and put us in a position where we can make a decision about what's the next best thing to do. So this adaptive exploration, then, the idea is to work with the entire area that you're trying to explore and use the measurements that you make to update your model of the entire scene. So in updating, we're going to use a Bayesian experimental design, trying to choose the most effective measurements to make. We're going to use some probabilistic models that allow us to reason about maybe not the perfect measurement or being in the exact right place, but still gain information from that. And then in terms of planning, we're going to use information theory to maximize our information gain or minimize the entropy about the site, and try to use some planners that have some foresight. This is all predicated on using rover instruments. The main thing we focus on is imaging spectroscopy. So these are devices that collect full reflectance data over a particular set of wavelengths. So you can think of it like an RGB image is giving you 3 channels. These devices are giving you hundreds of measurements throughout the electromagnetic spectrum. And from that continuous signal, we can actually identify material properties. So I have an image here of I have an example here of a hyperspectral image. Each pixel in this image is not just RG or B, but it's actually has a continuous spectra associated with it. So it's a data cube. We also want to know exactly where things are measured. So this hyperspectral image is spatially registered as well. One of the things to keep in mind is that any one of those pixels is probably not just one thing. It's not a pure mineral, a pure element. It's going to be a mixture of things. So part of the challenge here is that we need to unmix the signal in order to do reasoning about what to measure and to do classification. So we've put together a machine learning architecture for this. We learn features from the data, and we do that using an encoding architecture I'll describe in a moment. But the basic idea is, sorry, let me do this in the opposite order. So we're going to use a variational autoencoder. What that is a dimensionality reduction technique that allows us to take measurements from a spectrometer, imaging spectrometer, and compress them into a lower dimensional space, particularly a Gaussian process. We're going to use actually just 3 dimensions. So we'll start with something like 200 dimensions in our spectra. We'll encode that down into 3 dimensions, and then we'll decode it back up and reconstruct the original signal. So in this way, you can apply learning, supervised learning, and train your encoder and decoder. So why we do that is because there are too many channels in the spectra for us to pass all of those to a classifier. So we're going to do this compression. We're going to end up with independent, uncorrelated features in the Gaussian process, and we can then use those to reconstruct signal and classify. I can go into more detail on that and the questions, but the idea here of spatial spectral regression developed by Dave Thompson and others, is that you, again, go from the many dimensions of the imaging spectrometer signal down to a few feature dimensions. We don't know what these features are. They're nothing. This is just not a nonlinear combination of these features produces the original signal. So we have this compressed latent space. So what does that mean? Because we've encoded this as a Gaussian process, now we can reason about things like our uncertainty about areas in that model. We can calculate the entropy, which we can then use to guide where to sample. So for information gathering with our robot, then we, as I said, we calculate entropy and show that by sampling in places of higher entropy, we're better able to reduce the uncertainty in our map overall. So we developed a number of different planners. I'll talk about the 3 that we employed in this recent field experiment. Actually, I'm very happy that my master's student, Kevin Edelson, successfully presented his work last week, and will be going, he's at JPL now working on this, but we have some additional planners that are even more effective. But for simplicity, I'll just stick with this work here. So we compared a number of different graph search planners operating on entropy in order to maximize information. As a baseline, we just used a random sampler, a random planner that made a random decision where to sample next, stepping through the world. That gives us an idea of what just wandering around does, basically. A greedy strategy that looks ahead to determine what point in the reachable space is of highest value. And then a Monte Carlo tree search strategy, which looks ahead a number of steps. I think this work here is showing like a 4-step look ahead, but we did a parametric study about how much look ahead to use. We implemented these and we used data from Cooperite Hills, Nevada, both data that we had in advance for a simulation study, and then we went to the field and took nice pictures with drones to conduct some of these experiments live and validate our method. Why Cooperite Hills? It's a pretty awful place, but it is extremely well studied because for some reason there are more minerals packed into one tiny little area than just about any other place in the US. It's not far from Death Valley for those that are familiar with the Nevada area. So why that's important to us is we have excellent ground truth. So we actually have geologic maps that are registered to the meter scale. So when our robot then builds its model, we have something to compare against, and we can actually compute error on our modeling. So we started with a simulation study to test the software and to make sure things worked as we expected, I guess. We used data from the Avarice NG instrument, which flies on in this case, it was low altitude airplane that gave us that meter scale, high resolution spectra. Effectively the same as what you get on the ground. On the ground, you get a little bit higher resolution, but the data product looks the same. So we use that plus Aster data, which is low resolution, as our prior, and we're able to kind of simulate anywhere we wanted to sample in the site. So 3 different sites at Cooperite, the 3 different planners. We did 100 traverses of each planner, so 900 simulated paths. And what we were able to show was that here where you see on the left is the entropy as the simulated robot travels along. So the white dots are the path it's taking, the points that it chooses to take a measurement. If I can make that play one more time. We start with high entropy, and as the robot collects more samples, the entropy overall decreases. So 2 things to see here. First, the entropy over the whole area reduces, not just at the points where the measurements are made. And this is, again, because we have this spatial spectral regression to that Gaussian process. The other thing to see here on the right, I'll make it go one more time maybe, is that we start with high uncertainty around the spectral signal for each pixel. And then as we take more measurements of the robot, that uncertainty, the prediction is the dotted green line. You see it follows very closely with our ground truth from AVERS NG. That decreases dramatically, again, for two places that the robot never visited. So we're able to do this high resolution spectral reconstruction. All right, moving on. Okay, so another result from the simulation study, we were able to verify that reduction in entropy strongly correlates with reduction in the map error. So entropy is a good metric to use if you want to build accurate maps. We also showed with statistical significance that the MCTS planner outperforms a short look ahead and a random planner. Not too surprising there. I don't have a detail here, but I would note that the MCTS planner takes longer to execute than the greedy planner, but this new work that we're doing with an ergodic planner actually outperforms even the greedy planner. Well, it performs at the same level as the greedy planner, which is about 2 orders of magnitude faster than MCTS. So we're super excited to get that out in the field and try it, because it will run in real time as the robot rolls along. So here, just a little bit of data from, I know I'm out of time here, but from one of the field sites. So our Inform Planner MCTS does outperform. So this is data collected by the robot as it traverses. You can see the paths it followed there over on the right. And again, planning with MCTS gets us a greater reduction in entropy and greater reduction in the map error. I'll take a second here maybe to play this last one on the right. On the right here, you see the geologic map. So this is actually the classifier running on the output of that spectral reconstruction to classify the primary geologic unit in each of these areas. And again, we've built a map over this. It's a 1 kilometer square area, and we visited about 20 sites in order to build that map. Slide advance is not cooperating. Okay. And lastly, we were able to do mineral identification, again, because our spectral reconstruction, the dotted blue is tightly correlating with both the AVERS NG, and also for some of this work, we went and made field measurements with an ASD that's a handheld spectrometer in the field. And again, you see all of these things correlate pretty tightly, and we're able to identify the primary minerals at the site. Lastly, we've been applying this in a couple other areas. This is just an example using data from CRISM, and I can't think of the other instrument on Mars. It's a high resolution instrument. Here we're building geologic maps, obviously simulating. And you can see we're able to reduce entropy and find different geologic units. On Mars, we're doing some work, same idea, same process. Here we're mapping coral, algae, and sand using PRISM, which is an oceanographic imaging spectrometer. And on the right, you see ultimately we're able to closely predict the different classes of material relative to ground truth. Again, only takes a few samples in order to map over a large area. So with that, I'll stop. Thank you very much. And I'm excited to put science autonomy on all of the robots that we've seen here today. I think then we can really get some exciting science done. And thank you very much.
Thank you, David. So where are we? I've just got a quick question. Given this global planner for a robot, do you think you could combine this with a mobility planner that takes into account the terrain topology and the various locomotion cost functions so that the robot could both explore the terrain effectively, but also do it safely?
Yes, that's a very insightful question there. Somewhere buried in one of the slides, I mentioned that what we're doing for terrain in these experiments are to set some thresholds. So just some constraints on maximum slope, for example, and essentially exclude those areas, forcing the planner to choose a next best place to take a measurement. So I guess we'd avoid all the repelling activities and find our way around to get something good enough. However, that's definitely a direction we're heading. I have a new graduate student who is looking into multi-parameter optimization techniques and whether we can reason more continuously about things like traversability. Also power, we were thinking about some lunar applications where you'd want to consider illumination and power as one of your considerations while you're planning your sampling strategy.